So, hi everyone, and welcome to today's ilifu training session. Today's session is the second in the series of advanced training topics, and the focus of the session is going to be on applications and software environments on ilifu. I just wanted to introduce the support team. I am Jeremy, and the other members of the team that are here today is Dane Kennedy and Jordan Collier, I believe, who will be joining us in a moment. And Mike Curran is also here, if you want to say hi, Mike. Mike is support for ilifu operations.
Hey, what's up, everyone?
We also have, thanks, Mike. We also have a guest speaker today, Gerrit, Botha, who is the senior bioinformatician at computational biology at UCT. Thank you, Gerrit, for joining us today. And Gerrit will be presenting on the topic of Nextflow. So I just wanted to take the opportunity to speak about the support channels that we have available. So for help and support related questions, you can contact us at support@ilifu.ac.za. We have our user documentation at docs.ilifu.ac.za, where you can find a lot of the information that we'll be covering today, as well as information from the previous two training sessions. We also have a status page, which users can check if they are experiencing any issues. And if the issue is not mentioned on the status page, please do follow up with us and raise a ticket through the support email. And finally, I just wanted to mention that these training videos are recorded and we make them available from the ilifu website. The URL is indicated on the slides. So in terms of the topics that we'll be covering today, I'm going to be speaking about Singularity containers, as well as Python virtual environments. And then I'll also speak about how to use these software stacks or Python software stacks as kernels in JupyterHub. Dane will then speak about R containers and RStudio. Gerrit will talk about Nextflow, and then Jordan Collier will speak about the CARTA astronomy visualization software, as well as information about the SARAO archive. So the training session should run for about 50 minutes, and then we've allocated for about 10 minutes after the session for questions. So I'm going to dive right into Singularity. So we spoke about this originally in the basic training. We described how Singularity containers encapsulate software on the ilifu cluster. So a container is a single container image file and includes all the software libraries, packages that are required to run a workflow application or pipeline. So containers are useful as they allow the software to be accessed from anywhere on the ilifu cluster. So from any of the compute nodes or from the standalone nodes. And they also allow for research groups to share software stacks amongst their members and also with members of other research groups. And another aspect of Singularity, which is containers, which is really great, is that they form an important component of science reproducibility because you have all your software in one place and it's easy to reproduce the container. So in terms of sourcing a container, so we have a number of containers that we support. Most of these are astronomy containers, and you can find them information about these from the documentation, the user documentation, under software, supported software environments and then available containers. On this list is the astronomy containers, and you can use the arrows next to the container to drop down and expand the information and see what is available inside the individual containers. I'd like to just point out the source finding Python 3 container, which is quite extensive. This is also known as the AstroPy container on Jupyter and in the container directory on ilifu. And it has a large, it's like a monolithic container. It contains a large number of machine learning and astronomy specific Python libraries, and also a large number of astronomy software packages that are available in this container. So We also support or provide the service of building containers for research groups. So if you need a container developed for your group, if you want specific software for running on ilifu, please do contact us at the support and we can help you build a container. We already support a number of containers for different projects, including both astronomy and bioinformatics. So most of the containers can be found at the directory for software containers on the ilifu file system. So usually it'll be the group such as IDIA or ilifu and /software/containers. And you can go and have a look at what containers are already available. Another option for sourcing a container is from a repository online, for example, Docker Hub and Singularity Hub. These are repositories of container images. For example, for Docker Hub, they have a lot of Docker images available, and it's a very well supported platform. So although Docker is not supported on ilifu, you can very easily convert a Docker container into a Singularity container, which you would be able to run on ilifu. So to do this, you can run Singularity pull, you specify the repo Docker and the specific repo that you're looking for in the image name, and this will pull that container and convert it into a Singularity where you run the command. You're also able to use the repos to build containers. So in the second example, Singularity build container name, here you can specify the destination name of the container when pulling from a repo. So this information is available from the Singularity documentation from the link listed on the slides. So while we provide support for research groups and users to help build containers, you are also able to build your own containers if this is something that interests you. So building a container does require root access on the system where you're building it. So users aren't able to build containers on ilifu, which is why we provide the service, but users are able to build containers on their personal computers and then migrate them to the ilifu storage to run on the cluster. So just to keep in mind that Singularity is backwards compatible, so you could build containers using Singularity 2.6 or Singularity 3, but just remember to check what version we currently support on ilifu. At the moment it's 3.5.2, so I wouldn't suggest going beyond that version when migrating or building a container yourself, because you might run into conflict issues. So the different ways to build a container include, as mentioned, you can build from an existing repo. So you could even upload a Docker image onto Docker Hub and then pull it as a Singularity container onto ilifu. That's one option. You can also build a container from an existing container. So you can add software and packages or update a container by building on top of an existing container. But the most common and recommended way to build a container is from a definition file. This is like a recipe on how to produce a container, or the steps that you go through. So this is recommended as it allows for reproducibility. If you have the script defined and you can build it, and then if you run or build the container at a later stage, it should generally produce the same container environment. So I'm going to go through the definition file as an example of how to build your own container. So definition file is just a recipe. The recipe contains different sections, but ultimately it's just a step-by-step setup of setting up the software environment. So the definition file contains a header section, and this defines the source of the container or the container operating system. So for example, I've got the first example is sourcing or selecting Ubuntu as the operating system inside the container. And here we specifically selected Bionic. We've targeted the archive Ubuntu mirror URL for the setup files. You could, in this instance, switch Bionic to Xenial or Trusty or other legacy versions of Ubuntu. And this is useful if you want to install legacy software which is not compatible with the later Ubuntu versions. So this is an example where containers are particularly useful. The second example is here I'm building from a local image. So if I already have a container and I want to add software packages to this container, I can build from the container, and I could just put the path of that original container in the header file. So the file section of a recipe is where you describe files that you want copied from your underlying operating system directory structure into the container. This step will occur before the installation, which would occur in post, percentage post section. So this is if you require maybe a zip of a data product, a tarball, or sorry, not of data products, but of data that you require in order to install software, and if there were scripts or something that you had on your operating system that you wanted to run during the setup, you could copy them into the container environment through this step. So the first file one just shows where the source and destination are the same, the source of the file and where you want to copy it to in the container. And then file 2 example is where you want to copy file 2 from your operating system, your base operating directory structure, into /opt inside the container. So the source and the destination is different in the second example. So the environment section is used to set up your environmental variables. These would be invoked when the container environment is launched by the users. So when you're calling the container with shell or exec to run the container with a script, these environment variables are set when the container is launched. And finally, the post section. So this is where the installation of software occurs. So here you would list the libraries, the packages, and it's very similar to installing software on like your Ubuntu virtual machine or your laptop. So you're stepping through the stages of installing the dependencies, downloading a particular file, untarring, and then running a script, etc. So this is basically the recipe of setting up the software environment. So, for example, in the example on the slides, I am installing or adding a repository to my Ubuntu. I'm installing a number of packages such as the wget, git, and other libraries that might be necessary. I'm downloading Anaconda and installing it, and then I'm pip installing using the pip from Anaconda or the Python environment to install several packages. And at the end of the setup, I am removing the install file because you don't need that anymore, and just cleaning up the container. Yeah, so there are a number of other sections that are useful. So there's run, script, apt, label, and help. These are useful to customize the container further. Specifically, run, script, and app allow you to customize how the container behaves when you execute it. But more information about this can be found in the user documentation. I'm not going to cover this further. So here is the definition file as a single file. So in full, you can see the header, the environment, post, and run script. I just want to point out that the environment section, that isn't called prior to setup. So any environment variables that need to be set up during the post stage must be included in the post section. And that is why you can see the export path Anaconda is also repeated prior to using Python from Anaconda to install. So that's just one thing to keep in mind when building a container. So yeah, once you have your definition file constructed, you can then build the container by running the command Singularity build, and then you specify the container name that you wish to use, and you point to the definition file that you've written. So here, an example, I'm building a container called machine ml astro.sing, and I'm pointing to the definition file as an example. So if you do need assistance with this or would like our help or advice, please do contact us at support. So one of the useful things if you have built your own container is, especially if you've used if you set up a software stack that is compatible with Jupyter environment, you're able to use your container and that software stack as a kernel in Jupyter for development. So in order to do that, the first line Jupyter kernel spec list will just show you what kernels you currently have available, and there are some default ones that are already set up for you. But if you want to use a container as your custom kernel, you have to place a kernel.json file at the location indicated. So as an example, I'm creating the machine learning kernel. I'll put it at users jeremy.local share Jupyter kernel, etc. And so the contents of that kernel file is quite specific. So this is an example of the layout. So you would specify the kernel name, the language, and the how you would invoke that kernel. This is an example where the kernel is inside a container. We call the command that would lead us to this kernel. In this case, we're calling Singularity executing, and we're executing the container that we built, and we're specifying Python as the Python interpreter, or the path to Python to reach the interpreter, and we're calling the IPython kernel. So if you create this file and place it at the specific directory for the kernels, then you will be able to use this kernel. Here I've shown the machine learning kernel that I created in my Jupyter Lab instance on ilifu cluster. So another alternative to containers is for setting up a Python package or Python environment is using Python virtual environment. So what this does is that it creates an isolated Python installation within a specified directory. And you're able to then quickly put together a Python environment with specialized packages or workflow that you would like to test. So I'd just like to point out that we have had a number of issues with Python package conflicts on ilifu, and this occurs when a user uses pip install -- user to install a Python package. And this sometimes causes conflicts between package versions with the operating system Python or the Python that is currently in the containers. So in order to avoid this, we would recommend using virtualenv to create a virtual Python environment, as this keeps it isolated and will prevent these kind of conflicts from occurring. So what's useful about virtualenv versus the Python venv is that you're able to specify a version of Python that you would like to use, such as Python 2.7 or Python 3, Python 3.6. One of the caveats about using a Python virtual environment, however, is that if a Python package that you wish to install requires specific dependencies in terms of libraries on the base operating system, if these aren't available on the compute nodes in ilifu, then you're going to get an error when trying to install those packages. In this case, I would suggest then going the container route, installing the libraries that are required, and then using Python inside that container environment. So it's pretty simple to set up a virtual environment. It's just for absolute basic one, you just run the command virtualenv and then the path to the directory where you want to place the virtual environment. So there are a number of parameters that you can use as well. You can check what's available by running virtualenv -- help. And some examples of parameters that are available is like parameter Python. You can specify which Python interpreter you would like to use. Another kind of important parameter is system site packages. So this is a choice you have to make as to whether your virtual environment has access to the underlying operating system site packages or not. So you can kind of customize how isolated your Python environment is. So running through an example, here I'm creating a virtual Python environment, running virtualenv and specifying to build a, well, at the directory ml, and this is just the path where I've chosen. So once it's built, you need to, in order to invoke the environment, you have to run the activate script, which is located always at the directory destination /bin/activate. So you would source this. At this point, if I type which Python in the command line, I will get the output that is pointing to the Python at this bin location or directory inside my virtual environment. And in that case, I can then pip install the packages that I want to use, and it would install into this directory structure. And then to exit the virtual environment, you can just type deactivate. So just last point is that you can also use virtual environments, the Python virtual environment, as a kernel. In this case, you as a kernel in the JupyterHub environment. So you would source or activate your Python environment. If you have Jupyter installed, pip install Jupyter, you could then run ipython kernel install name, and you can give it a specific name. And this will place a kernel.json file that is correctly customized at the correct directory structure. And then you'll have your kernel available in the JupyterHub lab. So that is what I wanted to cover about Python virtual environments. So I'm going to hand over to Dane Kennedy, who will speak about R.
Hello everyone. Got to figure out how to share my screen. Is that working?
Yeah, I can see the window with the presentation, Dane.
And now you can see the presentation.
Exactly.
Super. Okay, I won't keep you guys for long. I'm just going to speak a little bit mainly about how to use R and some other little bits that you need to use it effectively. So to start off with, I want to talk about modules. All the stuff I'm talking about is in the documentation. So modules allow one to run software on the cluster without having to know how it's installed. So it's a system for maintaining, from our point of view, software and different versions of software. So we can have multiple versions of R or Python all running concurrently, all installed on the system. And this allows you to use them fairly simply. So does my mouse show up when I do this?
Yeah, it does, Dane.
Okay, cool. Essentially, all you need to know is two commands, and that is module avail, and this brings up a list of software that I've installed, and it's quite new on ilifu, so there's not much to show, but I've installed latest version of R, together with Python and a recent version of OpenMPI. So here's an example where I was running on the cluster. R wasn't available. I tried to run R and it gave me command not found. I wrote module add, and then I gave the name of the module, which was shown here, and then R started working. Behind the scenes, if you're interested, all it does is when you say module add R, it sets up the environment, so it modifies your path so it can find the binary. If you have aliases or need access to libraries within a package, that all gets set up. So that's something that we do on the back end. If you say module show, and then your module, it can actually show you exactly what it's doing behind the scenes if you're interested. But mostly you don't really need to know that. And the other thing I want to first talk about before I get on to actually using R is modifying your SSH config. This is mainly just a useful way of simplifying your connection to the cluster so you don't have to write in a long command. So here, this is an example of what I've got in my own file. And the important line is here, host slurm.ilifu. And when I want to connect to the slurm cluster, I simply say ssh slurm.ilifu, and then it connects for me, and it works in a hierarchical way because it sees that it's got slurm.ilifu.act.za there, and then it looks at this above config and matches that pattern over there. So it knows my username, it knows which SSH key to use, and it does these other forward agent, which forwards your keys from your machine, your PC, onto the cluster. And that's important for RStudio, which I'll show you in a moment. So then I'll talk about how you use R, and then I'll just do a quick live demo, which is sure to fail, but we'll try. You might hear someone shouting timber in a moment, and that's my 3-year-old getting very enthusiastic about being a lumberjack. I apologize about that, but I can hear him. I think we've already covered how one runs jobs on the cluster. So you can run interactive jobs, or you can run within an SBatch file, or one can run in an environment like Jupyter. So the first example I've given here is how one might run within an interactive job, and I've kind of shown exactly what one needs to do. So it's the normal kind of, I keep doing that, srun command, and that gets you onto a worker node. And then to get access to R, you would use the module add, which I showed earlier, and then you have access to R in interactive job. I think the preferred way of actually using the cluster is in an SBatch file, because then you aren't wasting time typing out commands. That's the main reason. But it's very much the same thing. You have your normal kind of reserve, what you need. And the important thing to do is just to remember to do module add and the model name, and then you can run your job. And here's just an example of what's in that covid.r file, which I'll load in a moment in an RStudio, because it's quite fun. Yes, I think that's reasonably straightforward. Please contact me if that's confusing, or read the documentation, but I think it's easy. The more confusing thing is RStudio, because it requires a few additional steps. And it's covered in the documentation, but I think it's probably better just to show you live. So, Jeremy, can you confirm that's showing the right window now, my terminal?
Yeah, I can see your terminal, Dane.
Okay, cool. So first thing to do is to connect to the cluster. So we're SSHing to slurm.ilifu.act.za, and then hopefully it's going to allow me in. So that's the same login screen you guys will get. Then I'm going to start an interactive job. So I'm going to say srun, I need a single node.
Then at the moment, the text is at the bottom of the screen for us, so it's not visible to me.
Is it not visible? Is that better?
Yeah, that's perfect.
So we're going to do srun nodes 1 p2i bash. Is that sufficient? And now we're on a node, and we check which modules are available, and it gives us a nice little list. I've got some additional things here. The CBio guys will see this, but nobody else will see this set of things. Most other people's lists will start here. So I'm going to add the module for R 3.6.3. I didn't say add. So I'll get back to the top. So module add R 3.6.3. And now it's working. We can get into R. And there we've got R. But that's not the exciting bit. I'm going to start RStudio. This is in the documentation, but for RStudio, one has to specify a password. And the reason for this is that on the node, when you start RStudio in this manner, it essentially listens on the node on a specific port. And anyone could potentially connect to that node and get access to your RStudio environment. And in doing that, they can get access to all your files. So it's quite important to use a password. This won't show up to anyone, so you can make it something exciting. You'll all see my password now. I'm going to trust you not to abuse it. It's not going to be up for long. I'm just going to make it ABCD 1 through 4. And then we run our server. And then it should just give us a little bit of information. It says our server is running on this port. And the second step is where your SSH config is important, because we open up a new terminal. So this is running on our own PCs. Let me just split. Sorry. And now, so I'm running back on my PC this command, and I'm going to SSH into the node I was running on before, which is SLWork 109. And the reason I can SSH directly to that is because I've set up my SSH config. And then I need to do 2 more options. This tells it to listen on my local computer at a given port. I'll show you why that's necessary now. And then I must go to port 49357 on the compute node. So I run that command. And with any luck, it connects. So you can see now in that terminal, I'm connected to SLWork 109.
And I think you wrote 6.7 and not 5.7.
Oh, did I? 493. Oh, okay, sorry. Okay, so now we're listening there. And now all I need to do is go to my browser. And I go to that port I chose, which was 8080. Of course, it's a live demo. Two seconds, debug.
Can you say local, or do you need local host?
What did I say?
Local.
I said local host. That should. Where did I say local?
On the SSH prompt, you've got local.
Did I?
Yeah.
Ah, thank you, Mike.
Sure.
Okay, now this should work. No. I'm going to choose a different port. I suspect I've messed that up. Haha. Okay. So now it's just, if you've used RStudio before, this should look familiar. Remind myself what I used for password. And then some RStudio loveliness should appear. Yeah, sorry, I've got quite a small font. Does that look okay? Can you read it?
I can see it fine, Dane.
Let me zoom in a bit. Oh, the other thing I wanted to mention is installing packages should just work in the normal way. So if we wanted to say, I was looking at a package earlier this morning, install packages, COVID-19.analytics, is that right? And it should make a comment about where it's doing it. I swear this was faster this morning when I tested it. Okay, yeah, we've got a package. Can you see the bottom of that, Jeremy? Not sure.
Yeah, I can do.
Okay, cool. And then we can do something like use that library we just loaded. And then do a summary. And it should download to COVID-19. Data, say. And it's downloaded some data. So there were some nice graphics that I found earlier. Now I've got the command wrong. But essentially that's all I had to say. But please contact me if you have more problems. Ah, there we go. There's a graphic. Yeah, I think we can move on to Gerrit. Thanks.
Thanks, Dane. Gerrit Botha is going to speak about the Nextflow software.
Thanks, Jeremy. Can you see this?
Yes, I can.
Okay, cool. All right.
Gerrit, the participants' images in front. Great, that's perfect.
I'm going to move this. Okay. Okay, guys. I'm going to give a quick talk about Nextflow introduction. So Nextflow is a workflow management tool that's both a language and a workflow engine. It gives you the possibility to do fast prototyping by simply putting together tasks and using existing scripts. You can also create a pipeline to design to run locally on your on your system, and then port it over to SGE, LSF, PBS, or Slurm cluster. And it also has support for AWS, Batch, GCP, or Google Cloud Platform and Kubernetes. It's ideal for high throughput problems where you need to split by sample, chromosome, position, or iterate over a range of variables. It has Singularity and Docker support, so it allows for reproducibility. You can set your job wall time, memory, and core requirements can be specified in the Nextflow script. Overall, it has a good documentation and user support. And for today, I will go through example case to show you some of the Nextflow features. I will work with a 16S dataset of 15 samples, and I will run it through FastQC, which is a well-known bioinformatics tool to do QC reports on sequence data. And then I will collect all of the reports into one FastQC report or multi-QC report using multi-QC. Okay. So a Nextflow script are made by joining different processes. The processes are connected to each other with channels. So in this little script, you would see you have 3 sections where the one section you get information from the configuration file, some information of the process, and then there's the channel that's been created. So the channel is created with the from file pairs method, which creates a set of sample ID and forward and reverse reads. Then you've got your process, which is marked by process. In the process, you can specify and label your process, specify the number of CPUs and where the output directory should be. Your input is defined, and here you pull in your channel and push it to a sample ID and file variable. Then you've got a section where you've got your script, and in your script section you run your tool. So you've got your fastqc specifying the output directory, specifying the number of tasks, and specifying the forward read and the reverse read that it needs to operate on. And then your output is pushed also to a channel, which takes all of the zip files from the fastqc report. So operators allow you to connect channels together or transform channels. So in this process, so after we run fastqc, we run multiqc. In this process, you also have a label for your process. Output directory is defined. You define your input directory, your input channel. And here we've got an operator that's running on your channel. So the fastqc files channel is a channel with individual sets of reports, but with the collect operation, you put all of them into one list. So when you run multiqc, you can operate on all of the fastqc files and generate one fastqc output report, multiqc output report. So the Nextflow syntax has been developed to ease the writing of computational pipelines in a declarative manner. Nextflow can execute any piece of Groovy code or use any library of the Java virtual machine platform. So below here is some examples from Groovy, where you can set variables, set integers, set values from functions, set real values, set Boolean values, set strings. You can make lists, access lists, make dictionaries or maps. You can also create closures that's similar to Lambda function in Python, and also do conditional execution, regular expressions, and file output operations. So you can do all of this Groovy code within your Nextflow main script to manipulate your workflow as it goes. So with your main Nextflow script, you also have the configuration file where you do specifications for for settings happening in your main setting. So the configuration properties are defined in the Nextflow config file. So it's split it up in different scopes. So you've got the executor scope. In here, you specify the tag name or the job name. You've got the params scope where you specify the project name, the file path for the input reads and the output directory, and also the queue that it needs to use. Then in the profile scope, you specify different executors. So you can have a local executor where you run Nextflow on your local machine, or you run it on a Slurm cluster. So you say the executor is Slurm, you pull in the queue value from above. You also specify which container to use. So in this case, we use a Docker container, but we say Singularity needs to be enabled. So what happens is the Docker container is converted to Singularity. You also specify the process, memory, and CPU usage requirements for the default processes. So in this case, 4 gigs of RAM and 1 CPU. So Nextflow does a good job in reporting and tracing jobs resource usages. So you have your execution report, which is the HTML report with the total number of jobs, and then your visual summary reports for memory, CPU, IO usage, and execution times. You also have a trace report that's similar to the HTML report, but in a tabular format. You have a timeline report, which is a Gantt chart of all the jobs executed in the pipeline. You also can generate a DAG visualization. And there's also a Nextflow tower, which is a web service to provide real-time visualization of your workflow progress and resource usage. Caching and resuming is a very important feature of Nextflow. So with the -resume option, the workflow can be executed from where it got interrupted previously. And this feature is made possible by a caching feature, which generates a unique key by indexing the process script and the inputs. And then the key is used to identify unique outputs produced by the process execution. So for the setup on ilifu, we have a Java installation and a Nextflow installation that you can see in the path variable. If you use that, you also need to just set up your Java environmental variables and the Java command and Java home. We run Nextflow in an interactive node because it does consume memory, and you need to test on the size of your workflow how much memory it will consume. I find that it can take up to 48 gigs of RAM. Try to use Scratch as far as possible for your working directory. And if you're running big jobs, try to limit your workflow to 100 jobs in the queue and a resubmission rate of 10 jobs per minute. And that can be specified in the executor scope. So set the queue size to 100 and the submit rate limit to 10 jobs per minute. So if we just have a quick look at a run. So you, at the top, it's very small, but I hope you can see that. You will create an interactive job submission request, get onto a node, call Nextflow, specify where the log file should be, specify your config file, specify where the working directory is, specify your profile, and specify all of the reporting flags that needs to be run on your data. Then it will run, it will tell you, okay, yes, your jobs are running, and when it's completed, it will tell you when it pulls the Docker container. And then I try to rerun it again with the resume just to show you how it's been cached. So it picks up the data has been cached, so it just runs it on the cached data and then completes it. If you look into the queue manager, you would see your jobs being listed in the queue as it was labeled in your Nextflow configuration file. So with the project name, the RFQC label, and then the ID of the sample. If you look at your output directory, you would have all of your folders for each sample, and then a combined multi-QC report. If you look at the individual folders of the sample, you would get the FastQC reports. And then if you look at the working directory, you would find directories that consist of 2 characters, which is basically the hash of the process. And then a Singularity folder, which contains the Singularity image. In the process directory, you would find like hidden files that contains the command.run, which is the bash script, and the execution file. So if we just have a peek at the execution file, you'd see what ran on the node was fastqc minus our directory, the doc10 fastqc folder, using 2 processes, using the forward read and the reverse read. And then if you look at the folder, there's a forward read and a reverse read being staged into the directory, and the output directory is being created. So here is just the report of the multi-QC report, showing the individual reports from the FastQC report. Here is the trace report showing you the for each individual job that ran, how long it took, what percentage CPU it took, what the memory consumption was, and how much IO it consumed. Here's the Gantt chart showing you the processes that ran. So all of the FastQ jobs ran together, then the multi-QC job ran. Here's the DAG showing you just the workflow that we did: run FastQC, collected the files, ran multi-QC. And then this is the HTML report showing you box plots and whiskers for the CPU, memory, job duration, IO consumption. So some extra features that's available in Nextflow that's worth exploring. The Scratch directive allows you to process the working directory and a temp directory that is local to the node. And when the random string is provided to Scratch, the local memory of the execution node will be used as Scratch space. And in the DSL2 version 2, its modularization is allowed. So you can have your functions in separate Nextflow files and pull them into your main function file and pass the parameters between the two. So in this case, we have a main pipeline that will do alignment, mark duplicates, and base quality score recalibration. It will pull in some FASTQ files. It will process the alignment files, and then the output will be passed on to a mark duplicates module, and that output will then be passed on to a base quality score recalibration module. So it's a very nice additional feature in the version 2. So in terms of documentation, so the latest documentation is always a useful resource. There are some working examples in the awesome Nextflow page. And then NF Core has some workflows for standard protocols. And it's also worth looking at the recurrent implementation patterns used in Nextflow applications. So thank you.
Fantastic. Thank you very much, Gerrit, for going through the Nextflow software for us. Really appreciate it.
Pleasure, Jeremy.
We're going to move on with the last two topics, which is the CARTA astronomy visualization software and the SARAO archive information. Jordan Collier is going to take us through these sections. I know that we're running a little bit late on time, but I think it would be great to cover this information anyway.
Yeah, sounds good. I just need to claim the screen share.
Sure, I can do that.
So I propose that we just continue as planned, and that anyone that has to go can watch the recording later, which we'll make available on the ilifu website. And if you do have questions and you need to run off, please just type them in the chat, and we can cover those in this video, which you can watch later. And of course, as Jeremy said, you can always email support, and we can get back to you there. So that's right, I'm going to demonstrate CARTA. This is an astronomy visualization software. We've got the server version being hosted at IDIA, and it's a tool that's designed to deal with big data. And so it does all sorts of things that are necessary to do when considering big data, like tiled rendering and rendering only the current visible image rather than trying to render the whole image and then just show you a portion of it, lots of things like that. So there's all sorts of documentation on this, which I don't need to go through now, but you can find that here. Things like that only the CARTA share directory is visible within CARTA. So if you have files that you want to visualize, you have to put them there, ideally by converting them to HDF5 in this way. And then that means that your images will perform within CARTA much better due to various things that they do when converting to HDF5. So this is what happens when you connect to the CARTA server. So you log in with your Jupyter credentials, and by default the file browser will open. And so this puts you in the CARTA share directory in your user directory. For the first demonstration, I'm going to go to this top level, and you've also got groups for shared group data within various projects. I'm going to demonstrate an image I made from Julia Healy's Meerkat OpenTime data. This is something that I made with the IDIA pipeline. And so you can see, no, that's the wrong one, sorry. So it just pops up within this central widget here, and that's for the main image. Sorry, my computer's quite old, so it's probably performing much worse than it will for you. So each of these windows are widgets, and each of them can be pulled up by clicking on the buttons here, or you can go to view and select one of them from these various categories. And each of these has their own help, so you can just press the little question mark and it pulls up the help to the side there. And some of them also have their own settings, so you press the little gear and you can see some of the settings for that widget. You can also pull up the general help from the online manual in this way, and this just pulls up the documentation. You can also see the controls and shortcuts, also with shift question mark. And so this is various keyboard shortcuts that you can use while you're using CARTA. You can also pull up information about the file that's open, as well as its header. And for this panel, you can set the overlay settings, things to do with the numerics and the ticks and various overlay settings. And then there's also this preferences tab where you can set a whole bunch of things. You can also do dark mode in that preference menu, which is Shift D. And so these are all the kinds of settings that you may want to play with. There's by default this render config widget comes up, and this is where you can change the color map. So for instance, a popular one is cube helix. You can change the scaling to say log, and you can see these are like instantaneous transformations of the color scale and the transfer function. And that's because it's done on the front end. And so it's essentially an instantaneous operation and is one of those things, like I say, that's addressing the big data aspect. So there's no need to re-render all of the image data and send it across the server again, but it's just done on the front end. So it's instantaneous for the user. And so you can, of course, zoom in and out with the normal zooming. You can look at the X and Y axes. So by default, it follows your cursor, but you can freeze that with F, and it freezes on position. You could then zoom in on your X and Y line profiles. If you want, you can zoom right in, but perhaps you make a mistake and then you just hit the gear and you scroll down and you reset range. That goes back to the default. There's all sorts of configurable parameters for this. You could even save one of these plots. So you just click the little save, it exports this image, which you can then open, and you may be able to, sorry, just to confirm, you can see that. Just give a shout out if you can't see that plot showing there. And then you could even do the same for the image that's being shown. And so this could be something that you may want to put in a paper or something like that. And whatever's visible to you within CARTA is saved to that exported image. And so then I can draw regions. So that's with this button down here. There's all sorts of different regions I can draw. I'm going to do an ellipse, and I've set it up as corner to corner. And this is a configurable parameter. You can do like from the center outwards, but I've set it as corner to corner. I can double click on this and call it like target or something like that. And then this comes up in the region list as target. And so you can name all your regions so that you remember which is which. You can then lock this so I can't move that region. I can center on it with a little eyeball symbol. And then within this region, now that I've got it selected, it means it's active. So for instance, in this statistics widget, I can look at the statistics of the active region, or I can use the drop down to look at statistics of different regions. So this has all sorts of interesting statistics, including the flux density. So this is different to just the sum of pixels and is a useful value to know from within your regions. And then of course I can export those regions. I can choose CARTA format or DS9 format, world coordinate or pixel coordinate. By default it's world coordinate, and so if I load that into another image, it will also draw the region within the right position. And then for the next feature, I want to open a different image. So I'm going back to my user directory. I'm going to load in this quick look Laduma image that I made with the pipeline. And I'm going to append image, which doesn't overwrite what you have open, but it appends to it. And this is a CDFS image from the Atlas survey. And so in the animator, you can see I now have these two frames. And I've set it up so that by default it does the spatial matching, but you can also select that here. And so that means I can now toggle between these frames, and you'll see they'll be positionally matched. And so, for instance, I could look at some feature like this, and I could blink between them, and I can then compare those images. And so that's how you do the world coordinate system matching. I can also play with this contours tool, and this is, so for instance, if I want to draw contours from the Laduma image, there's all sorts of ways I can do this with different contour generators. If I just use the default for this demonstration, I can then apply those contours. I can change all sorts of things with smoothing and the color. I can even do it not as a single color, but a color map that changes depending on its strength. For this, I'm just going to do maybe, I guess, green contours. And then you can see I can then go to the next frame, and you can see those are overlaid as contours from the other image onto this image. So you can play with that tool. For the other features, I'd like to open a cube. So I'm going to go to this public directory, and Angus in his one has a Galfax cube. So this is a spectral line cube that also has all 4 Stokes axes. So these are for the polarization parameters. I'm going to load in an image that, a region that a set of regions that I created before. So I've drawn a polygon around this. You can see that. I've got 3 within my region list. I'm going to select the first of these. And you can see in this I have a whole bunch of channels. So I can step through channels here. I can play through the animator. And you can see I can also change Stokes channels. So this will much more quickly for most people except my computer go to Stokes Q and Stokes U. If I go back to I can look at, for instance, the Z profile through the selected region. So this is showing me as a function of frequency what the value within the pixels of that region are across frequency. And what I can also do is I can pull up this Stokes analysis widget, and this is showing, for instance, let me just go back to, okay, I'm not sure what's happened to the color here. Normally this is colored. Nonetheless, you can see that I've got the Stokes Q versus U plot for the selected region. And then you can see the same, but as a function of frequency. And so this is a tool that you can play with. You can also just do it for the cursor. So I can look at how this is changing for the different cursor positions. And normally this is shown as colored. I'm not sure why that's happening. I also meant to say with saving these figures, if you want to just export the data, you can do that. And it's a tab separated file. So you can then import that into your own plotting code that you can then plot in your own preferred way. And so that's how to use those different widgets for a cube. And then the last thing I want to show is just in the preferences for people using CARTA from afar. You could look at the performance settings. This is also useful for any kind of limited network connection. So you can do low bandwidth mode, which is quite useful. You can also play with these compression settings. Again, you can pull up the help to look at that, but this is for, in particular, people remotely using CARTA on IDIA, say from different countries. You can play with these settings to increase, to optimize your user experience. And you can see by hovering over the green dot here what your latency is, to see whether you've got a network issue that may mean that you want to play with these kinds of settings. So those are the features I want to demonstrate within CARTA. Next, I want to show the SARAO archive. And so this is a tool for transferring Meerkat data to third-party facilities like IDIA, or in fact to any kind of machine. And so this is what comes up when you log in. You must register on the archive in order to be able to do this. This is only really for PIs or nominated representatives for projects that want to push data to elsewhere. And so if you should be one of those people, the PI of your project should contact the archive once you have registered and should then ask for permission for you to be added. You must also have a project on IDIA that transferring data comes under, and so that we know what project to make the data available under. And so if you don't have one, you need to contact support, and ideally please notify us of your intention to transfer. So this is what comes up. You can look at all sorts of details about certain observations, but I just mainly want to demonstrate. So there's this push to IDIA button. It's blue when it hasn't been pushed. It's green when it is pushing. Sorry, green when it has been pushed, and orange when it is pushing. And you can also get a direct link. So you could do something like a wget on whatever machine, but that is quite slow. It doesn't use an efficient transfer service. So if you're pushing to IDIA, you should ideally push the button. And then you can even do a Redis database link and download the data in native format, but most people don't want to do this, so we don't suggest that unless you know what you're doing with, say, the tool CatDAO, or if you'd like to explore that, please contact us or the SARAO archive. Now I wanted to show you can configure the conversion to measurement set for data that's in 4K, 32K, or 1K channel resolution. Now I've documented a number of these things on the ilifu documentation page here. I've suggested the kinds of parameters that you may want to play with, and I've mentioned things like only single transfers are generally allowed at once, and that's because the SARAO archive sets a flag once you do transfer the data once, so that it prevents you from doing it again. But if you do have sufficient reason to do this, please, I guess, talk to us first, and we can see whether there might be a chance to do this, and I guess communicate that with SARAO for you. Furthermore, if you do manage to have a newer transfer able to be done, then it will by default overwrite the data. So if you, for instance, are trying to do a different selection of data and you try and transfer that as a second file, you would need to contact us so that we make sure it doesn't overwrite the previous data. And of course, they're in measurement set by default, but as I said, you can do other formats. It's just not recommended unless you need to do that and you know what you're doing. And so these are the parameters that you can use to configure the conversion. You can click on this link here to the cookbook, as well as this one here, to look at this flags field. So this is a field where you can set the level of flags that are applied. Now, as I've documented here, there was a change in November last year when the flags were updated to these three values. So control and monitoring, data lost, and ingest RFI. You can read what those categories are. But before then, the full set of flags were applied, and many people were experiencing raw data being flagged for even the target up to 30% or even 90%. And so this may be difficult to calibrate, and if you have data from this period, it may be worth looking at removing that and retransferring that so that you can get a better calibration. And so, yeah, you can read all about those parameters within this cookbook, for instance. It shows all the parameters. You can read about the flags within here. But generally, I think doing something like at least CAM and data lost is useful. Some people don't even like to use CAM. I think setting full polarization MS to false is good unless you need to do calibration of the full polarization correlations. You can play with selecting certain frequency ranges if, for instance, there's persistent interference that you know isn't useful to transfer. You can average channels, so if you're doing a continuum project, you can consider averaging 32 channels so that you get down to 1K resolution, which can be sufficient for certain continuum projects. You could consider only selecting HH and VV, which is XX and YY. This is similar to the false parameter, but I'm not sure whether it's necessary. I usually just do both. And then those are the main ones, as well as this auto correlation data. I think it's useful to exclude it since no one really needs to use those data for most projects. And so those are the kinds of parameters that I wanted to demonstrate. I'm just going to quickly check here that I've basically covered everything. I guess this quack one setting is useful so that you discard the first dump. This is the default for calibrated data as well. You can select these different defaults and it fills out these fields with certain defaults. And so I think that's everything that I had wanted to show. So I'm going to stop my screen share there.